KL divergence is nothing but just to compare two entropies and how are these two entropies are far apart from each other. So the distance, relative distance between them, between two distributions. So if we look at the information, let's say we have two distributions Q and P, right? We want to measure the difference in the information. So we just take the information of Q minus the information of P. And then from that we get the log P over Q. Okay, this is clear?
So P and Q are from
two different distributions.
Okay.
Yeah. Not related to each other.
Okay, not
it could be related.
It could be, yeah.
So this is clear. It's basically come from the measurement of information that we had earlier. In here, where we want to measure just the information of one distribution. So we want to find the difference between two probability distributions.
Okay.
Okay. And if we refer back to Shannon entropy, we have two machines with the probability of machine 1, let's say denoted by P, and probability of machine 2 denoted by Q. Therefore, if we want to find the distance between these two entropies, between Q and P, we just use the entropy and subtract them. It would result in this. Okay. So KL divergence is, we'll get to that. Sorry. So we now know how can we find the distance between two entropies. But KL divergence is not just the distance between two entropies, but it is the relative distance between two entropies.
Is expected value of the difference.
Yeah, but with relative to one
To
another.
one, yeah, exactly.
So this equation is 99% correct, I would say. But since we want to find KL divergence with respect to one probability, so given a distribution, we want to find distance between the new distribution from this distribution. So with relative to let's say in this case, with respect to P. So we want to find the distance from P to Q with respect to P.
Okay.
Okay? So now, if you can notice, it is no longer Q log Q minus P log P anymore, but it is the cross entropy between P and Q minus the entropy of P. Okay? So if we rearrange them, we get this, and this is Kubernetes derivations.
One question. Why do you want to know the distance between the entropies of these two distributions?
Why do you want to know the distance between these two distributions? We want to, well, in our case, we use this mostly to see if the distribution is changed given the new control variables. Let's say you change a parameter in the system, you get a new distribution, right? You want to see if new information can be gained by changing those variables. Okay, like for example, if I take my experiments, I have a probe probing over an audio. Okay, and my probe can change the thickness. I probe once, I probe twice, 3 times, I get distributions. And I would like to know if I change like the stiffness of my joint, would I get more information by comparing the distribution of, like, let's say x equal to 2, and if I change x equal to 4,
X being here.
like stiffness, for example, would I gain new information from that? Or if I don't get any information, I could just stop exploring, something like this.
By when you say more information means more accurate.
It doesn't mean more accurate.
No, yeah.
What does it mean?
It means that
Physical.
the necessity to explore more. Really.
I think your probe is a good example if you would, and just instead of the yes and no questions. I think that would, if you would explain how it works with
With his.
yeah,
Yeah.
so you're, that's
Okay. Yeah, but this case is a bit complex. I would say.
it is.
Yeah. So I didn't use this example as in the beginning, but I'll get to that later on. But as soon as you ask, I'll just explain it. So basically, we use Bayesian KR divergence in Bayesian inferencing to measure if we change one variables, do we get information? If not, we can just stop exploring. So by maximizing information gain, meaning that there are still some uncertainty in the system, in your observation or in your prediction. So in this case, I use it to predict the depth of the nodule. If you saw, right, if the Shannon entropy is at its maximum when there are a lot of uncertainty.
And they need also Bayesian inferencing to understand. So let's say you okay. Let's say you start with the probability distribution, okay? Okay, so he has a probe, and then he has a stiffness, and then he probes the tissue, and then every time he goes over the nodule, he gets a torque reading, okay? But every time he moves, he gets a slightly different torque, okay? Is that right? So every time he moves over the nodule at a given speed, at a given indentation, he gets a torque reading, right? In the force sensor. And then now you get torque readings all over, but when you pass over the nodule, you get a separate torque, which is like a peak, right?
Mhm.
And then if you sample that peak torque across trials, you get a distribution.
Okay.
Okay?
So we're saying trial 1, the torque was at this distance or at this stiffness?
At that for a given stiffness, for a given indentation, for a given speed, at this point you
This
get
point.
that torque,
Okay.
right? So,
Okay.
okay? So it's a conditional probability distribution. Now the problem is, now if I want to get better torque resolution, right?
That means you want to find exactly, you want
Exactly
the
where
point
is.
where
Yeah.
you're expecting to see a
Right?
change.
So let's say like I get now different torques now, right?
Yeah.
And then when I change the stiffness, what will happen to that distribution? Basically, that's the question. Okay. And then you start with some kind of a prior thing about your hypothesis is that, okay, so the nodule is there. Okay. I don't know. It is a flat distribution. Okay. Probability of finding the nodule, right? Can you write it like that? Probability of the depth of the nodule given my torque, speed, and indentation. Okay? We have a probability distribution. Now what we do is we let's say we start with the flat distribution. Okay? We don't know where it is. Depth is like something, it can be from 0 to infinity. Okay? And then when you have a likelihood function, right? So can you write it like? So that's the prior. And the likelihood is, so you have a given a d, you have a top, right?
No, because you don't know d. This is the likelihood function. Right?
No. So given a reading, how probable is that reading, right? Yeah, you're reading top, right? Yeah. So the likelihood is, so your prior is
My prior is just this.
probability of talk.
Yep. No, my prior is probability of the depth
Of the depth
given tau.
given talk. Yeah. So that is the prior.
That
so
is the prior.
what is below is the prior. And then the likelihood is the top reading given.
This is likelihood.
Yeah. Do you know that Bayesian thing?
No.
Okay. So I think you should.
I should cover it at some point later on.
Oh, later on.
Okay.
Because I didn't prepare.
So So we need that to. So basically, like we use basic inferencing to tune a prior assumption. We're using evidence. So evidence is likelihood, right?
This is quite difficult.
I think
It is
we should-
actually very easy.
But we should discuss. I think we should discuss not using this. You should discuss in a different, like maybe a simpler.
That's why I didn't want to jump into this.
No, now that we talked about it. So let's say you have a probability. You want to find the probability of the depth given some measurement, right? So I would say measurement. Okay.
The measurement being.
It can be talk.
Could be anything.
Any measurement. Right? This is the sensor reading and this is my hypothesis. Okay? And then basically you can expand this probability. Because you don't know this, you know only that, right? You can write this as P, you can invert that. You can say measurement given depth PD.
Should it be divided by PN?
Yeah, so it is the sum of PM, right? All the measurements, like, but because when you sum it up, like it goes to 1, right? For all the
So this is a mathematical expansion
of
the
the
left half.
PD given M, right? And then so we call this the prior assumption. Prior assumption of the depth. Okay. So that means like, so you can have this probability of, let's say, depth, and then I can say, okay, so I think the depth is distributed like that, somewhere there, but I'm not very sure. Okay.
But it could be entirely off.
It can be completely off, or it can be even flat.
In my case, we start with 2 to 5.
Okay. So you can say the cool thing about Bayesian is you can put your biases or whatever based on any speculation. You can start with some function. Based on newspaper readings, I think this is that. Fine, right? Okay? But it is just a hypothesis, right? Or somebody told me that it can be somewhere there. It is okay, right, to do this. But this is evidence, right? Given, like, you now read the measurements, right? This is true evidence. This is just speculation, right? So now you read values. And then you look at how probable is that measurement given my depth estimate, right? Is that right?
I'm sure it is.
Okay, so let's take another example. Let's take another example. I have a metal detector, right? I have a metal detector,
Natural bit.
right? And then I have a piece of nail here, right? Okay? Then I think my nail is somewhere there,
Okay.
right? I think that nail is buried under the ground somewhere there,
Okay.
okay? Now you move your metal detector, and then here, when the metal detector is there, you get a reading,
Okay.
okay? Or you get a peak, like
Yeah.
that sound peak
Yeah.
there, peak sound,
Yeah.
okay? And then when the metal detector is giving the peak sound, given the sensor characteristics, you know that it is highly probable that the nail is right under there, but it can be there or there or there,
Yes.
right? These purely the sensor characteristics,
Okay.
okay? Given the sensor characteristics, I can say, given if you think that the nail is there, this is the probability that my measurement is true.
Yes.
Okay? So, like when the depth is somewhere really there, my measurement probability increases,
Yeah.
given that distribution, right? So then what you do is, so you got a reading there, and then this is my sensor characteristics, and then you multiply that distribution and that distribution,
Okay.
right?
Okay.
Then you update your assumption,
Oh, that becomes the prior for the next.
the posterior, right?
Okay.
And the posterior distribution is neither that nor that. It shifts in probability, it shifts to the distribution which is thinner.
Yeah.
Okay? So the new expected value, new mean, sorry. Now the expected value of D is, right, the previous the prior, right, D prior times it's D prior times D prior divided by sigma, right? Sigma prior plus D times your likelihood, right? Divided by that sigma and then 1 upon sigma prior plus 1 upon sigma L. So this gives you what? D prior multiplied by sigma of L plus D L times sigma of prior divided by sigma. Yeah, that's it, right? Yes, right? So what happens is, if sigma likelihood is thinner, right, sharper, the whole thing shifts to that because it's weighted higher,
Okay.
right? The prior shifts to that. So, and then finally, your prior is also sharp and your likelihood is also sharp, right? And it settles down, right? Settles down to, the posterior settles down to, based on the more evidence you have, it settles down to something. Now the question is, each time the prior shifts to another distribution from P to Q, whether do you gain any information? Okay? Do you gain any information by taking a new measurement which shifts your probability distribution? Right? And then that is the information of the posterior minus the information of the prior, and then you can do that for different stiffness values, right? So, and whatever the control variable you have. And then for some control variables, this converges fast. And then after some time, you don't gain any information, you stop exploring.
Which means that your distribution is sharp enough to make an estimation.
Is that right?
for example, in the second reading, what did you change? You changed the position or the depth?
In my
Yeah, your assumption of the
I,
depth.
I changed the control variables to change the assumption.
The-
Thank you, Trish. I think it is clear.
It needs some background reading.
Yeah, I mean that note is good enough. You can just go through that.
I think this example is a lot clearer than
But it's, I think it's a very applicable and important thing to know actually where to stop your experiments, because what you're saying is very important. That
Yeah.
from now on, you don't need more experiments. You already,
Exactly.
you're not going to get a high resolution of the
you're not going to get.
So okay, divergence is giving you a quantified
Yeah.
measurement about the worthiness of doing more, collecting more data, or collecting more evidence.
I think I'm going to skip this example since this one is a lot better. So I'll just talk about the characteristics of KR divergence. Okay. Let's say if we have two, can do my interrupt yourself?
No.
His recording hopefully works.
Let me take a picture in the case.
How long did it take you to learn all of this probability and
Until today, I'm still learning. Well, I mean, it's not fair to.
I think Nadja started with kind of, as I can remember, like so you
I didn't even know what
exactly what
probability
probability is, and then he picked up so fast. And I think the important thing is that, I mean, for me, like I don't remember any equations. I just remember the physical meaning of things, and then I think that's how you picked up, right? Just the physical meaning. I don't know what, you know, like equations are not important.
Yeah.
I didn't do stat at school. This was my.
I think we our approach is right. So we look at theory as more applied.
Yes.
If we go back to our example, just to visualize how asymmetrical the KR divergence is. Let's say we have two machines as usual, in chemistry, with probability distribution Q and R, and this can produce 4 letters as I told you before. The probability of Q would be, in this case, 0.5, 0.5. That's 0.25. The probability of R again. So these are the probability of machine 2 and machine 3 in producing A, B, C, and D. Okay. And what do I mean by asymmetrical? Meaning that the KR divergence between from Q to R is not the same as from R to Q. It's confusing. So like let's say if you have point A and point B, I am now saying that the distance to go
Yeah.
from A to B is not the same as distance from B to A. This is okay.
I understood this paradox, but okay.
Okay. So one way of looking at this being, if like we have a point A and the surrounding point around A.
So this is a set with, and those dots are the probability distribution of its measures.
Like something in spaces.
Okay.
And we have point B. So if you ask A, is B very far away? A will say, because a lot of points are very close
Oh,
together.
yeah.
A will say that B is quite far away,
Yeah.
really far away. But if you ask B, if A is really far away,
No.
because most of the points are very far away from B. So you say, okay, it is far, but not very far.
Yeah.
So, but however the distance, so in chaos divergence we talk about relative distance. So with respect to which point of view, so the distance are different. Okay. This is just to explain what do we mean by relative with respect to each distribution. So if we want to measure the chaos divergence of Q with respect to R, in MATLAB we can begin with the probability of Q. Probability of machine tree. So it's essentially that's that. And we find now the chaos divergence of Q with respect to R. So we just say sum of this probability R. So now Q with respect to R. We get, this is the chaos divergence. However, if we say, if you want to find the chaos divergence of R with respect to Q, so we did Q with respect to R, with respect to Q. So we should not get the same answer, right? So the distance between Q and R with respect to R is 0.0803. However, the distance between these two distributions with respect to Q are different. So this is the asymmetrical properties of chaos divergence, this one.
So for example, if you want to go back to this metal detection example, so Q would be, so you're probing the face with a metal detector, and Q, the point where you have 5 is like an XY coordinate, so that point is giving the high probability of finding the level underground.
Yep.
And R,
So let's say that Q is your prior distribution and R is your current distribution. You compare these two. It's not the same as you. So you compare the current with respect to prior, right?
so for example, you have another metal detector, now you went, you charge the batteries, you come again and you get R.
Mm-hmm.
This is correct?
Yep, yep. It's not the same as you take the prior and then you calculate the divergence of current with respect, calculate the divergence of the prior with respect to current observations.
Okay.
Yep. So this is just the properties. And another property is that scale divergence is always equal or more than 0. Why is that? Because let's say if you keep observing a system. Let's say this is your prior distribution, your current distribution. Now, in the next observation, you get the same. This is your current. So if you take prior, what do you get if they are the same? So log of 1. Yeah, so it's going to be 0. So it's not negative.
And so this is the divergence is now 0.
Yep, because now you don't have any new information.
Exactly.
So this is what happens when it converges. So in my experiment, if it approaches to 0, I do not need to explore any further. But in my experiment, I set the threshold to like 0.0005. And I think Thrish explains about maximizing information gain using scale divergence in Bayesian already. So, like for example, in this case, we have a probability distribution of force given x equals 0 and some parameters I. So upon next observation, we change the value of x to some new values. Therefore, our new distribution becomes this. So we ask, by changing x based on the new distribution, would we learn more about f, or would we gain any more information by changing the value of x from 0 to 2, for example? So I want to show you this very interesting thing. So first I create physics as spatial one. Create a reading of. Do you want to take a photo of this? Or no?
Yeah.
If I measure force, like from my example, this x is these stiffness parameters. And F is the force rating. And in my setup, x can vary from 1 to 20. Okay. And let's say we take 25 readings. We're going to get 25 force for each x values, 1 to 20. We take 25 trials. Okay. our readings, we will have 25 rows with 20 columns. Each column corresponds to one distribution. So sum to one. This is I created using the command called ranfixsum. It's not a standard MATLAB command, but it's available in the MATLAB website. You can download it. So basically, it generates a probability distribution of as many as you want, like as many columns as you want, as many samples as you want. So in this case, I say 25 samples with 20 distribution, with the sum of the distribution to 1, and these are like the parameters to the distributions.
So at the end, the summation of the column has to be 1.
Yep. So the sum of each column is 1. Now, I want to see if by changing the x around a lot, do I get information? And which x would produce the highest information? I'll give you the code for this one. So I'll just randomly move around, like from one point to another, from another to another, comparing this distribution across each other. And I find the mean information gain. So what I found from these randomly generated numbers, I found that x around here or here give me the highest information. For example, this is just the example of how you would measure the information gain. Okay. But in practice, we don't use this one. So,
What are different colors in the left graph?
the left graph is just automatically generated by moving this around, by
Okay.
changing x.
By changing it.
Yeah, comparing them.
So each color is for one color,
From one pairs.
one pair. Okay.
And as I say, from x1 to x2 is not the same as from x2 to x1.
Okay.
So I have, I don't know, 400 lines there.
Okay. Just a question. Between your 25 readings, you have different readings because
No, it doesn't, I'm sorry, it's not 25 trials. It could be any number of trials, but it's just
Okay.
the 25 points. Of
okay, yeah.
Sorry.
But in ideal case, all 25 trials should be identical, right? Should be similar.
Then you don't have a distribution.
Yes,
Yeah, right.
but you have
You
distribution
would have only
because
have one.
yes, you have distribution because you have uncertainty.
Yeah.
Whole
Any system has uncertainty.
yes.
If they are so uncertain, you get one and it's all 0, 0, 0.
Yes.
This is just a distribution.
Yes.
So then x 0 to 20 is, those are changes. So
There was
that 20 means like it's an increase from 0 to 20.
Yeah.
It's not exact the absolute value of 20.
Yeah, it's 20. Yeah, the number of.
No, it is that x 20
Mhm.
is not number 20. It is a change from 0 to 20, right?
Yeah, it's the change from moving all the points to 20.
Yeah, okay,
Yeah,
points
it's-
to 20.
Yeah. So this corresponding to each line corresponding to moving from 1 to 20, moving from 2 to 20, like 3 to 20, 19, up to 19 to 20.
Yeah.
And each time you come.
So by
you come back
changing,
there,
what do you gain? That's the question, right?
Yep.
So if you change everything to 5, that is that
Yep.
that
So
5.
this is the average. This is not clear, but yeah, the average, and you may get the highest information from there. But yeah.
So on the left-hand side, each graph is the KL divergence between
Yeah.
randomly
Yeah.
chosen columns.
So when you have most flexible probe, you have better information, right?
Not necessarily.
Not necessarily, right?
Not the more flexible, but
Something. If x0 means I don't know.
But
flexibility.
it is certainly better than you have only a fixed stiffness probe, yeah. or static stiffness probe. Let's say you cannot change the stiffness, then you get always the same distribution every time.
So that is why Nadja is trying to explain, like, if you look at humans, how they do it, they change from soft to stiff and then stiff to soft, and then what are they trying to gain while they are probing? Like, they don't probe like that all the time. They do various things, right? And then what are they doing? And there is no biological explanation to that right now. And then this is by far the only, right? As far as we know, the only explanation to the biology.
So
They are trying to gain information, and then once they don't gain any information anymore, they stop the probe and then take a decision. Okay, this is where the nodule is.
Human might be doing some kind of similar Bayesian inferencing in the
Yeah.
brain.
And then Nadja shows that, like, within on average 5 trials, you
Less
can-
than 5.
less than
3
5 trials, 4, 5, you can converge.
Mhm.
5 trials were probing the entire
Mm.
path.
Mm.
But with different like, values of control variables.
Speed, yeah.
I just randomly changed.
Did it match with the readings you have based on our experiments? Yeah,
From the humans experiment, I use humans data in order to control the stiffness. So I basically extract the average EMG signals and see how average human movement pattern of the not movement, co-contraction pattern, and then map that to the stiffness control.
I see. Okay, from this graph, how did you conclude that 5 trials are optimal?
Not from this graph, from Bayesian inferencing.
Okay.
I use information gain in order to determine if the estimation is sufficient.
Okay.
So meaning that from parallel to current, you don't get any information or any new information anymore. So which means that they converge.
Yeah, so the funny finding is, it doesn't matter how you move around. As far as I move around, it converges, right? Faster.
Currently I don't find any significant or
And then it tallies with the
Generic
human
pattern.
thing, and the humans don't follow a specific pattern. So they just move around. So, like at a behavioral level, they just randomly behave, but at a information level, they steadily converge.
Yeah.
It's nice, right?
Yes. There was a talk in iGraph. They had a probe trying to find nodule. They used this information gain to guide the probe basically. There was a nice video showing that, for example.
From I told you.
Who?
What's her name? I think it's from Carnegie Mellon.
I think so.
He came and talked to you, right?
Yeah, I talked to her already.
Okay.
But what they use exactly like Bayesian inferencing.
Yeah, but for a different thing.
Yeah, for
To-
different things.
To
Yeah.
know where to probe.
Yes.
Yeah.
To know where is the probe or
To
No,
know
to know
where
where to
next.
go.
okay, yeah, where to go next? Yes, yes.
Yeah.
Completely different. It does not describe the behavior or suggest any specific pattern.
Yeah. But this shows that somehow we are doing.
This is internal, that is more external
Yeah,
behavior they're
exactly.
looking at.
Yes, yes. This is
Maybe we can combine and then do a joint paper at some point. So
that was something completely different. Yeah, I understand.
But
was
in a way,
guiding the
like
probe, but
similar
this one-
approach.
as far as they cite our papers.
As far as this, what?
They cite our paper.
Yes.
And then we cite their paper.
It's actually at some point you can tell the human how to probe
Yeah.
Yep, but
because there may be other methods around, but
it is not very easy to control your flow contraction
yeah,
to like an
So
absolute
we can
value.
inform the training protocols.
yes, yes.
So student training protocols and medicine.
Yeah.
Right. So that is one of the questions the thesis committee will ask you, the review. You write it like, so what is this thesis contributing? This informs the training policy, practice, or training practice of medical doctors or something like that.
And you can ask a doctor to find the nodule in his own way, and then you ask him, okay, do it as I said to you, and ask him which way you found it better.
Well,
maybe.
it depends, right? Because doctor has been doing that for long.
Yes, yes,
They have like million set of likelihood
yeah.
in their brain if we use the same, if we follow the same Bayesian inferencing. But if we ask them to change the way they probe to our finding, let's say they will just have only like 1 or 2 or 3 likelihood or mapping in their brain. So I'm not sure if
If that's
yeah.
Can you write your likelihood function to see the way you use primitives?
Our likelihood is what this is the likelihood.
Okay, so these likelihood functions, you call them primitives, right?
Yep. So these are obtained from the primitive. So in
Yeah, so Nanichai does that thing, right? So that that sensor I taught about the metal detector. So now that metal detector has a template likelihood function, right? So if it gives me this peak, my probability of finding the nail around it is this, right? So likewise, what he does is he collects data for different depths, known depths, right? And then known indentations, known velocities, and known stiffnesses, and then collects the torque, and then he accumulates for a known thing. What is my torque distribution, right? And then when he gets the data, torque data, he looks at the probability, likelihood of all the known things. Okay, and then he looks at the information. You do the Bayesian basically for all the primitives, right?
No, because yep.
All the primitives and then you pick the one.
But given these 3 control variables, because we know these 3 control variables.
Yeah, those
Yep.
For a non-control, those variables, you pick for that known thing, you pick one primitive.
3 primitives.
Why
Because,
3 primitives?
because we do not.
Oh, so you pick 3 primitives for 3 depths, for possible depths. And then you calculate you pick the one which gives you the highest
No,
likelihood?
no. So this will be a distribution of 3 numbers, right?
Okay,
Depending on the depth.
right.
Could be 0.25, 0.5. And then I times it with the prior.
Okay, you multiply by and then you get 3 posteriors.
Yeah.
And then what do you do?
And then we compare this distribution with the prior
Okay.
in order to assess if there is information given.
So you have 3 KL divergence values. You have 1 prior and 3 posteriors.
No, we compare each term. We have 1 prior, 1 posterior.
Okay.
Yep. This is the distribution. It's not the absolute value. Because our posterior, when we start, we have like 0.33. Right?
That's a prior.
Yep. When we times that together.
So this is the likelihood.
Yep, this is the likelihood.
Okay, so you get 3 posteriors. And then you calculate 3 KL divergences for the 3 posteriors.
I computed only 1 cable divergence.
Or you take that whole thing as a distribution?
Yeah, they have to be taken as a distribution. Because they are
But
the only
where I'm lost is you have 3 likelihood functions, right? And then what do you do with the
3 likelihood functions.
For a given array, given V, given I, you have 3 depths.
Yeah, and those, because you have only 1 top reading, right?
So, but that one top reading can be evaluated for 3 depths.
Yep, and it becomes the probability distribution, like as you want. So this is,
Okay, so that talk for that depth, this is that probability. That talk, that depth is that probability. Okay, so it is a probability distribution of depth again. Right, so now there's one distribution, one part. Okay, right. I see. Right. So then if you have more experience or more depths like in prior experience, and then you have a smoother distribution basically.
exactly.
So that's what he said about a surgeon's memory. Right? They have thousands of different scenarios in their mind, and our hypothesis is that is creating a smoother distribution than this. Right?
That's why it might not work by just telling the doctor to follow our probing strategy, because they have trained in different ways and they know how to recruit them and things differently.
So then the likelihood function learning is another process, right? So given the ground truth, like how can you update the likelihood? I think we can formulate this whole thing as a deep learning method,
Okay.
because it's a very multi-layer thing.
Mm.
Right? Let's formulate it later.
Just could you please explain again the right chart?
Yep.
How was it generated?
Well, it's this, just the mean
One of those, or it was one of those.
No, it's the
The
mean
Are you,
of
are you okay, Hasta, now?
the
You
mean
fine?
of each.
Clear? No questions?
Just show
So if you have a doubt, like ask the question. Ask questions now.
as I said, just I wrote this because in the code that I will give you, just want to show how can we do the coding.
So, just as a suggestion, can we have another tutorial focused on Bayesian functions and
Yeah, that's what we
exponentials?
planned as well.
Yes.
Yeah.
Thanks.
Next week.
No, it is really, really important to have a deeper understanding of this. This is it's very frequently used.
Mr. Thrish, I need to leave at 4 o'clock.
Okay, sure, sure.
I think I'm
Yeah.
a bit selfish, could you not continue with other stuff so that I could.
No, it's fine. So we will continue.
We're done with
So
this.
he's done. So next time we will continue more on Bayesian.
Who is next?
Who is next?
Who's next week?
I think Elham or you,
No, I don't found my thing.
but we could shift.
That's fine. We will mix it up. Like I'll come in between and talk about Bayesian or something.
Well,
Yeah.
I can talk about if.
So there's a
what-
separate book called The Bayesian Brain. I had that.
I mean, let's see what everyone says, but my suggestion is that let's stay on one topic maybe.
Oh, follow the trend.
Yeah,
So continue with Bayesian because we are in dynamics and static.
because that's a different topic.
Yes,
I think.
yes, yes.
So
So,
no one put in the.
So I think I don't know. I mean, I can talk about Gaussian mixture regression or something. Like what we learned, the tutorial was amazing. It's really nice.
Yeah.
Yeah.
Yeah, and the way Natasha did it was very interactive.
Mm-hmm.
I'm gonna do the things, the examples myself.
Okay.
Okay, yeah. So next week, Natasha will continue, or will you?
Not the time.
Natasha will continue. Okay.
Yeah, that's a big word. If you can talk about Bayesian, then.
Wait and do
Yeah.
first. I'll give a notice by Friday or Monday night.
Not Monday is too late.
Or Friday, like by the weekend.
I had a book. I'll give you.
Yeah, I have that book too.
You have that book, The Bayesian
Bayesian
Brain.
Brain.
Okay.
Nothing is in the calendar. Did you make notes in the
Oh,
calendar?
that is the
I
book.
didn't make note on the
I
calendar,
think
I
you
just
gave
took a
me.
picture
Okay.
and I think I forwarded the picture to Thrish's Google group, like what we had on the board.
Yeah. Okay. Fine.
Did you?
Yeah, I think if you can follow that.
Okay, remember
Maybe do a chapter.
I remember.
And then.
So next week, Bayesian thing, right?
Mhm.
Yeah, because Thrish was also going to make something about machine learning.
Yeah.
Do you
I mean,
remember?
it's basically these
The
stuff.
same
Like
thing.
Yeah,
this,
that's what I was saying.
Yeah.
like,
No, it's fine.
can
So
we
let
combine them?
what I do is whenever somebody talks, I will come in between
Yep.
and then fill things up, right? So,
Yeah, thank you so much.
Okay.
I'll put it in the
if
calendar.
not, have you done karma filtering?
Oh, that would be great.
Well, I did, so,
You did, right?
yeah, an extended one.
No, Bayesian karma filtering.
No.
Yeah. So if you
Okay.
in Bayesian Brain, the book it has it talks about filtering, Bayesian inferencing. Bayesian is filtering, right? You saw that, right? So you have a very wide distribution, and then you converge to a narrow
Okay.
distribution, which is filtering. Okay. So that's basically that's it. Evidence-based filtering.
Okay.
Karma filtering is nothing but evidence-based filtering.
Okay.
Right? So
It would be great to have a tutorial on Karma
Yeah.
filtering.
okay, right.
I don't know.
So I'll just jump in and then talk, and then we'll come to next time. We'll come to Bayesian karma filtering. So build up from Bayesian inferencing to all the way up to Bayesian karma filtering.
Okay, good.
Like 15 minutes.
Okay.
Yeah.
All right. Cool. So and then we'll be really thorough in math. So if you have any questions, just ask. Just stop and ask. This is really important.